So there are philosophers who will take it as sufficient to have time that you have both before and after relations, what they call B relations, and um, your so your causal sets obviously have something like that relation defined on them. What I'm wondering is really sort of like an elementary question, which is just something like, um, to what extent does the um, so you have these, for example, you have periods in your or regions in your cosmological model where time breaks down in a sense, and I'm wondering how much of the traditional way that people have thought about time breaks down in um, for those causal sets, if that makes sense.
Yeah, but well, I'm not a philosopher of time,
Yeah,
and I
sure.
don't know, but it maybe it's fair to say that there's at least two. I mean, at least time and general relativity seems to me to have two aspects. One is order, and the other is duration.
Okay.
And to in a causal set, order is retained, but there is no duration. I don't know whether that so.
So I think
Ask
that's
me
really
again.
interesting. Yeah, right. I mean, that's why the other, I guess that's why the other person asked the question, asked about how you get metrical structure from because you have to get back metrical structure at some level of description, even though you
Oh, right.
mentioned some
Okay.
level,
So
yeah.
yeah. Okay. So yeah. So there are two, at least two scenarios. You know, in the same causal set, you might have part of the causal set has a continuum approximation, and part of it doesn't. So in the part that does, you have to get back metrical information, and the you could say that the Penrose-Hawking-Malamud theorem says that if you have order and you have scale,
Mhm.
then you can get back all of the full metric. So there you have order, or you always have order, but you also, if there's a continuum approximation, then you get scale by counting. So for example, you could tell how long a particular chain, a maximal chain between two causal set elements is just by count the length, and so you then that would be duration as well, approximately.
Yeah, sure.
But in the parts of the causal set which are not manifold like, you don't have metric, there's no continuum approximation, there is just order. That's all. There's no, and yeah, you don't need to recover anything because it's not manifold like. It's it's a realm beyond our ken. It's beyond the reach of our experiments to date. So yeah, and there it's just the idea is that the physics is pure order.
Question about the quantum side of this. I kind of think I can guess what the answer looks like, but I'm wondering how to relate the last comments you made about quantum mechanics to the sort of initial diagrams you were drawing, which looked like a sort of univocal space-time with manifoldy regions and then causal regions that don't emit a manifold description and then non-manifoldy regions. Presumably, my path integral, if I do this quantum mechanically, is going to include very different causal sets that, for instance, go non-manifoldy at very different places or to very different degrees, and the whole thing is being put to superposition. So does that complicate the situation in any particular way, or in practice, can I just assume there's enough decoherence that you can pretend the system's stochastic when you're treating things on these scales?
Yes, in principle, it complicates things, and I mean, I can't even point to, the usual, toy models of decoherence of dust grains by the, microwave background to say, yes, there will be decoherence between macroscopically different, between causal sets which have macroscopically different continuum approximations. although one would, I mean, of course, we hope so. And, you know, it may be, I mean, what we would like, I think, is a picture in which the causal sets which contribute significantly to the path integral all they agree on the epochs of continuum-like behavior. So they're approximated by the same continuum space-time, but they're hugely different in the deep quantum bits. And that doesn't matter because it's deep quantum bits and we don't need to get any continuum description there. But yeah, whether that is what the quantum dynamics will give us once we have it, yeah, obviously I'm hoping so, but yeah, we don't know.
So, I mean, when you say contribute to the path integral, do you mean like contribute at all, or contribute when you're focusing on a particular region? I mean, are you expecting that somehow the dynamics is such there just won't be any significant weight on trajectories that don't all fall within one particular classical description, or is it going to kind of break down into different classical descriptions and it's just that they're going to deviate from each other, so we might as well pretend it's stochastic?
It seems very unlikely that it's going to. They're going to. There's just going to be one class of one continuum space-time, and they're all going to be close to that.
Yeah.
So I think we are going to have to appeal to decoherence between what I call events and what people in the decoherent histories literature call coarse-grained histories. So so we would need to expect some of that. Yeah.
Okay. Thanks.
So I have a question about the dynamics for past infinite causal sets you've been thinking about recently. And one remark you made at the very beginning when you started to talk about these ideas was that if you think of if you approach that problem by sort of starting in the middle, as it were, and then alternating, adding events to the future and the past, then you would lose the possible identification of that growth process with some sort of becoming or a passage of time or something like that. And I was a little bit surprised to hear that, because at the end of the article I wrote with Craig Callender about 5 years ago, we speculated about this, and the sort of the idea that we sketched there would be that in this case you would in fact end up with two different epochs where you have becoming toward the normal one, towards the future, and then the past one sort of prior to the Big Bang. There would also be a sort of an epoch of becoming away, in a way directed away from that initial moment, so that what you would end up with would be sort of two epochs of becoming. And the fact that you alternate between them doesn't really matter, because you might as well have chosen to sort of, label your birthing sequence with just the even numbers or the odd numbers or something like that. It's still going to be in each of these two separate domains. It's going to be a perfectly well-ordered sequence of growth, which I think you can individually associate with a sense of becoming or a passage of time, even though, of course, in a way you lose the sort of the global one, I suppose. But that seems to me, ideas like this seem to me perfectly viable. So what do you think about this?
Oh, thank you, Chris. I should have known about your work with Craig, so apologies. Yes, so I'm an old stick in the mud when it comes to time, I suppose, in the sense that I just think there's one direction for it. So what you're describing, I think, is that there's just two there's a direction, forwards and a direction backwards from this Big Bang. So in that sense, I think I wouldn't say then that this picture that I was basing my discussion on, that there's an epoch and then a punctuation and then another epoch, and that epoch is after the the one before. I think that's just not what you can't use those words and also have becoming, I think, away from the, upwards away from the Big Bang and downwards away from the Big Bang. At least I find that, I think that's just a different kind of picture.
Mm-hmm. Yeah, I agree about that. I think the interpretation of what I proposed would then, that the right interpretation would be something like the birth of twin universes rather than some sort of transition from an earlier epoch through the Big Bang into a sort of a later epoch. And there is, of course, the question whether you can have something like a growth dynamics, a generalized form of growth dynamics, in the sense that you have a truly infinite, totally ordered, complete sort of model of becoming, past infinite and future infinite. But I think, once you start to think about this, and this is what fascinates me about this material, is that there's so many, possible models that you could end up with, some of which are not obviously phenomenologically distinct from what you would expect for our own universe. So how are you going to, for instance, distinguish, the single past finite universe we seem to inhabit from the birth of a twin universe or something like that, or a triplet universe, or so all of a sudden you have all these options.
One thing I should perhaps mention is that it's not quite what you've been asking, but one thing Bruno and Stav tried to look at, I think they're both here, by the way, at least they said that they would come, but I can't see who's here, so I think they're... So they looked at a possibility of a growth model in which the causal set elements can be born anywhere. So our alternating dynamics, is it alternates past and future, and sort of grows from the top and grows from the bottom. But if you don't make such a condition, you can just have a causal set element being born in the middle, in between two causal elements that already exist. And of course, that's a reasonable thing to look at and to try. But the problem with that was that there was no way to take the limit. So there's no way to run that process to the end and get a causal set that the process is an infinite causal set that process is tending to. That's the problem with that. I mean, if you only want to grow a finite universe, a finite causal set, that's fine. But if you want to run something which produces for you an infinite causal set, then we couldn't make that work. So it seemed like that wasn't an option. That you did need to add things to the past and the, to the top and the bottom, which is it's the fact that the causal relation is a binary relation. It's not a triple of points that are somehow related. It's a pair of points which are related. It's a binary relation on the set. So there's only ever there's before and after. There's above and below, and yeah, that's it.